Good morning, Astronomy Lab students. Here we are now to discuss why you took that data pertaining to the culmination time of Fomalhaut each night and what we're going to do with that data. So it's really about the difference between the solar and sidereal day. When you think of the day, the length of time that we call the day, you're really usually thinking about the solar day, which is how long it takes. It's the amount of time between noon on one day and noon the next day. So, roughly speaking, how long it takes the sun to appear to go around the Earth. Of course, we know that everything in the sky looks like it's going around in circles because the Earth is rotating. So, let's look more carefully at that rotation. Here's planet Earth. And suppose you are standing at point A, looking sort of over your head. I guess this would be over your head if you're at the equator. So this would be noon. If you're on the other side of the Earth, smack dab in the middle of the dark side, the unilluminated half of the Earth, that would be midnight. So here you are at noon on some particular day, and we know that the Earth is doing this all the time. The Earth is rotating or spinning, but as it does that, it also revolves or orbits the sun. So we've got those two simultaneous motions, rotation and orbit. So let's imagine that we advance time by roughly 24 hours. So the Earth has moved a little bit in its orbit around the sun. It's scooted just a little bit. Now, if you think about it, the Earth goes around the sun in about 365 days. And we know that a circle can be chopped into 360 degrees. 365, 360, those numbers are very close. So roughly, the Earth sweeps out 1 degree per day. So a day later, this line that goes from the sun to the Earth has swept out an angle of approximately 1 degree. Now, look carefully at this part of the diagram. They've indicated that the Earth has turned exactly once. So your body, which was sticking out vertically from the surface of the Earth, if the Earth really rotates once, you've come back around to your initial orientation. And you'll notice that you're now not facing at the sun directly. You're a little off from the sun. And that is because the Earth has scooted a little bit in its orbit. So in order to bring you back into alignment with the sun so that you're looking at the sun, the Earth would have to rotate just a little bit further. And that would take a little bit more time. So the time required to bring you from facing the sun at noon to facing the sun again at noon the next day, that time is a little bit greater than the time it takes merely for the Earth to turn once. And that is the difference between the so-called solar and sidereal days. So the solar day, again, that's the one we're familiar with. That's from noon to noon. That's how long it takes the sun to appear to go around us once in the sky. Our daily life is based on that motion. We go to bed at roughly the same time every night and get up at roughly the same time. Well, on average, we do that. But the Earth actually takes less than 24 hours to spin once, and that amount of time is called the sidereal day. The amount of time for for the Earth merely to rotate once is called the sidereal day. It's kind of an awkwardly spelled word there. And it might be worth remembering that it's 23 hours, 56 minutes, and 4 seconds. Now, seconds, those are chump change for most purposes. So if you just ignore that 4 seconds, 23 hours and 56 minutes is 4 minutes less than 24 hours. Another 4 minutes would put you up at 24 hours. So a good number to memorize is that it takes the Earth about 4 minutes less to turn once than it does for the sun to appear to go around once. In other words, the sidereal day is about 4 minutes shorter than the solar day. You may be wondering, how come I didn't know this? I've gone through 20 plus years of life and I never knew that the Earth actually takes less than 24 hours to turn. That's because you wouldn't notice unless you were paying very careful attention to the stars, which you should have been doing these last 2 weeks or week and a half at this point. That's what this lab is about. If you pay attention to the stars, you would notice that they take less than 24 hours to come back to their position the day before. Here's a nice little animation that I pulled up on YouTube. There are some others on YouTube that are also very informative. So if you really want to understand this, do some exploring. Okay, so that was kind of quick and a little subtle, but watch carefully the orientation of the Earth. You'll notice that between this point and the next point where they draw a line off in the same direction, the Earth turns once. It turns through 360 degrees exactly, right there. So it's now in the exact same orientation that it was before. So again, if this line represents a line through your body as you stand vertically on the Earth, down here, the line through your body would have been pointed at the sun. That's noon. Now it's not pointed at the sun. It's a little before noon, in fact. So right here, they're showing, let me back up a few seconds. They're showing that the Earth has to turn just a little bit further, a little bit further to once again point you, if you're the vertical line, at the sun. And that extra amount of time is about 4 minutes. And if we'd like to know more precisely, you could just Google what's the length of the sidereal day. Hang on a second. Here it is, 23 hours, 56 minutes, and 4.1 seconds. Look at that. They know the amount of time it takes Earth to rotate to the nearest tenth of a second. In fact, they know it even more precisely than that. If you do some more Googling, try Wikipedia, I believe they've got measurements of the length of the day out to the hundredth of a second, maybe even the thousandth of a second. And that shouldn't be surprising because we've had atomic clocks for decades now, and atomic clocks can measure time to the nearest millionth, billionth of a second. So if astronomers are monitoring Earth's rotational speed carefully, let's say on Monday, this number is 4.1 seconds, and then on Tuesday, the length of the day was 4.10002 seconds, they can probably detect that. Minute changes in the rotational speed of the Earth. So we're just trying to confirm here in this lab the difference between the sidereal day and the solar day, roughly. We're going for that 4 minutes and hopefully these 4 seconds as well. Or I shouldn't say 4 seconds. Okay, so let's look at this right now. How many minutes and seconds would you need to add to this interval of time, the sidereal day, to get back to 24 full hours? Well, if you add 3 minutes to 56, that would bring you up to 59 minutes. So we have to add 3 minutes for sure. And what would you have to add to 4 seconds to get back up to another 60 seconds? Because again, 59 minutes plus 60 seconds would be the full 60 minutes and 23 hours. That's 24 hours. So 60 minus 4 is 56 seconds. So evidently, if you add 3 minutes and 56 seconds to the sidereal day, you get to 24 hours, which is the solar day. I was saying 4 minutes a moment ago. That was an approximation. It's more like 3 minutes and 56 seconds. That's the number that you're hoping to recover from this lab. It doesn't have to be exact. You just want to get somewhat close to 3 minutes and 56 seconds. Here's a nice simulation from the NAP website, Nebraska Astronomy Applet Project. We've got a solar time clock and a sidereal time clock. I'm not going to pay too much attention to the clocks here. Let's look at the graphic. Never mind these markings around the perimeter. That has to do with basically longitude on the celestial sphere. So here's planet Earth with you standing on it. You would be experiencing noon if you were on that side of the Earth exactly. And we know that Earth is turning. It's going around in circles. Well, you're going around in circles as the entire planet orbits the sun. So I'm going to click on this button a few times. This is advance time by 1 sidereal day. So every time I hit this button, you'll see that planet Earth rotates through 360 degrees. And if I do that enough times, it becomes apparent that this person is no longer aligned with the direction to the sun. In other words, they're no longer at the time noon. So here's one sidereal day into the future. Earth definitely rotated once. It's difficult to tell, but they've also scooted the planet a little forward in its orbit. I'm just going to keep tapping this, and you'll see now the Earth is definitely moving along its orbit, but each time I tap this button, it's rotating by exactly 360 degrees. And they are now no longer facing noon. So I don't know how many times I've tapped that button. Let's pretend it's 7 times. If I just advanced time by 7 sidereal days, you can see that is not the same as 7 solar days. Because if you start out at noon, I'll go back here, if you start out at noon, 12 o'clock noon, and advance time by 7 solar days, that's 1 week into the future, and you'll be back at noon, which means you should still be facing the sun, but we were not facing the sun. So this time, I'll advance by 1 solar day, something like 7 times. 2, 3, 4, 5. And if you watch, every time I hit that button, the Earth turns through a little bit more than 360 degrees, just a little bit extra to bring the person back into alignment with the sun. In other words, so they're still at noon. So mess around with that simulation if you're still not getting it. Now, of course, we should take a look in Stellarium. The next best thing to actually doing this in real life. Okay, it happens to be morning right now where I am. I would like to put the sun on the meridian. So first I'll tap semicolon, there's the meridian. I'll tap L a couple times, maybe Shift L to make small adjustments in the rate of time. And I'd like to put the sun right on top of the meridian. That's pretty good. Now you can't see the stars during the day because the sunlight, the scattered sunlight, overwhelms the light from the stars. But the stars are up there. If you could turn off the atmosphere, letter A, you would see the stars. So I want to find a star that also happens to be on or very near the meridian, and then we'll look down here at the time and examine the difference between the sidereal day and the solar day. So as I scan up and down the sky, I'm not seeing any star that's right on top of the meridian. However, if I zoom in here, there is this star that's pretty darn close. Good luck pronouncing this. I had to rehearse this, and I still don't know how to do it. Zubinul Ganubi. Zubinul Ganubi, that's the best I can do. Never heard of the star, Zubinul Ganubi. And is it the star closest to the sun? Well, only at this particular time. Remember, the sun wanders against the background of the stars. It moves along the ecliptic throughout the year. Okay, so I'm going to pause time. In fact, the sun is getting away from me. Get back here. Come back to the meridian, Mr. Sun. I think, is my program getting frozen here? There we go, right about, tap K. If you tap K again, you can freeze time. See, now the seconds are no longer ticking by. Okay, so let's look at the difference between advancing time by 1 solar day and 1 sidereal day. I will start with the solar day. The solar day is basically 24 hours. So that's just the, on your keyboard, that's the plus and minus signs. If I tap plus once, I will advance time by 1 solar day. That will bring the sun right back to where it is presently. So it's like we're fast forwarding, the sun's going to go, well, it will appear to go around the Earth and come right back to the meridian. And look at the time here, 11:66, that's in the morning, 44. Those numbers should not change on a 24-hour time scale. So here I go. I'm going to tap plus once. Notice how the date changes to November 7th. But the hour, minute, and second didn't change because I went ahead by 24 hours. And we see that the sun is right where it was, but that star has moved. That star has come around 360 degrees and some change, a little bit extra. Let's do it again. I'll hit plus. Now it's November 8th, same time. The sun is in the same place. So every solar day, the sun comes back to its starting point. But the stars have gone around once and a little bit extra. Why? Because the stars don't actually take 24 hours to go around once. They only take something like 23 hours and 56 minutes. So in those last 4 minutes of the solar day, the star continues to move across the sky. Again, it's back to the fact that not only is the Earth spinning, it's also orbiting. Did I say the sun? Not only is the Earth spinning, it's also orbiting the sun. And if you want to understand the difference, just go back to those animations. Okay, every time I hit plus, the sun is back where it started on the meridian, but the star has moved farther. Zubul Ganubi. We're also seeing the other behavior that we examined earlier in this lab, which is the fact that the altitude of the sun is decreasing on each successive day. That's because we're in the fall, approaching the winter solstice. Hey, the winter solstice happens right after the semester ends. So if you keep using your clinometer, you'll find right after the semester that the sun stops getting lower in the sky every day, then it'll start to go back up. Yay! Okay, let me go back to where I was, November 6th. And now let's advance time by one sidereal day at a time. And a sidereal day is less than 24 hours again. It's the amount of time it takes the Earth to turn once, roughly 23 hours, 56 minutes. And to do that, I can hold down Alt on the keyboard. And that's the amount of time, again, for the Earth to rotate once. So if the Earth spins once, everything in the sky that's super far away, like the stars, they should come right back to their starting positions. So here I go. And take a look at the time, 11:36:44. Here I go, Alt plus. Now check that out. The star didn't move because the Earth has just turned once. So everything that's at a fixed position in the sky came right back to where it started. The sun, though, has not quite made it back to the meridian because the sun needs 24 hours to do that, and I only advanced time by something like 23 hours and 56 minutes. You can see that down here. It was, I think, 11:36 before. Now it's more like 11:32. I'll do the same thing again. I hold down Alt, I hit the plus sign, and Zubinul Ganubi has not moved. The sun is even farther behind. So I think you're seeing how this works. Because what you did in the lab was observe Fomalhaut. You observed the time at which Fomalhaut culminates, and you found that it's a little bit later each day. And unfortunately, right now in this demonstration, I had the sun on the meridian. Let me speed up time a little bit and put Zubinul Ganubi. It's too much fun. Zubinul Ganubi on the meridian. So this would be the time at which Zubinul Ganubi culminates. Let's observe on this day, that's about 11:31. When does it next culminate? On the following day? Well, that's when it's right back in this position. That would be one sidereal day later. So I'll remind you once again, on this day, November 8th, it's 11:31. Let me advance one sidereal day. Alt plus. There's Zubinul Ganubi. Whoa, there's two Zubinul Ganubis. So they're back on the meridian, but now it's 11:27. So that star has culminated roughly 4 minutes earlier than it did the day before. Now it's 11:27. What about the next sidereal day? Alt plus. The next day, November 10th, it will culminate at 11:23. This is really what you're doing with Fomalhaut. If you write down, as you should be doing, if you write down the time at which Fomalhaut culminates every night, then you're really marking the time of successive sidereal days. Okay, let's go back to the spreadsheet now. Right now we're discussing this second block. This is the second part of the lab. We've already talked about what to do with the solar altitude. Now I rewrote here, instead of Fomalhaut, I went with Sirius because I didn't want you to just lift the data for a different star. So here's some roughly correct data for the culmination of Sirius. So on October 29th, Sirius culminates at about 4 a.m. 6 minutes. So suppose I had gone out at 4 a.m. every night and observed the time at which Sirius crosses the meridian. That would be pretty easy to do because Sirius is so darn bright. And I was realizing that there will be a number of days missing from your data because of cloud cover. That's probably the biggest challenge to taking astronomical observation or making astronomical observations. Okay. Now, if I had some precise instruments, because you guys just did the method where you put two rocks in a line, and that's obviously not ultra precise. If we were in an observatory with something called a transit circle, we could make much more precise measurements of the time of culmination, easily down to the nearest second. So we would have three columns for the hour, the minute, and the second of time, not degrees. But what you guys are doing, you'll be lucky to get it to the nearest minute. You should be able to get it to within a minute or two. So the idea is that you would round to the nearest minute. Like if it was 4 hours, 6 minutes, and 58 seconds. Maybe that would just be rounded to 4 hours and 7 minutes instead of 6. In any case, now that I've got this data, I would like to graph this. I want to graph the time of culmination versus the day. We've got 14 days, hopefully, of observation. But I'd like to put that time in what I will call, just for this lab, the minute number. So this is not a widely used term. I'm only using it for this lab. The minute number of culmination will be just the number of minutes that have passed since midnight. So basically, at what time does Sirius culminate for you guys, Fomalhaut, in minutes? Well, every hour has 60 minutes. So what I'll do is this minute number would equal, I'm clicking on the cell for the number of hours, 4 hours times 60 minutes per hour. So that will convert those 4 hours into 240 minutes plus the extra minutes in this column. And then I hit enter. Okay, so 4:06 a.m. That's what this time is, 4:06. That's the same as saying minute number 246. So on October 29th, Sirius culminated 246 minutes into the day, meaning 246 minutes after midnight. And to repeat that calculation, you've seen this before, I can hover over the lower right corner and double click or just click and drag. And all of these times will be converted into minute numbers. And you see that the star is definitely culminating earlier and earlier each night. Now, if you look carefully, the difference between these two times is 4 minutes. Same here, 4 minutes. So for the most part, it looks like 4 minutes. But we already know, isn't it more like 3 minutes and 56 seconds? Look at this, though. There's a jump of 6 minutes here. That seems a little suspicious. Yeah, a jump of 6 minutes here, 3 minutes here. So you are going to have small errors in every one of your observations because you're out there with two rocks trying to estimate when it crosses the meridian. There's obviously error there. Sometimes you're going to record the culmination a little bit early, sometimes a little bit late. But the idea is if you've actually taken measurements for close to 2 weeks, those errors will tend to cancel each other out. And we should be able to get some sort of average number from the whole thing. And to do that, we'll use a graph. You've already had some experience graphing in Excel, so let's do it again. Just in case Excel guesses correctly about which of these numbers I want to graph, I'm going to click on this column. We go up to Insert. I'm going to get the zoom stuff out of the way here. We'll go with the chart, Scatter Chart. No connect the dots, just a scatter chart. And I have no idea what this junk is. Excel is making some guess about what I want to plot, and that guess is wrong. So right-click, go to Select Data, and just get rid of these series that they've assumed we want to graph. Remove. All right, we'll start over. Add a data series. Series name. I'll just call it minute number, comma, for the Sirius culmination. That word always makes me think of the movie American Pie. There's a scene with the lacrosse coaches where one of the coaches says, "Today represents the culmination of all these months of hard work," and the assistant coach just chimes in, "Culmination." X values, that's the horizontal value. That would be the day. So I'm going to click and drag through these 14 numbers, just the numbers 1 through 14. I'll hit Tab to go to the next field. and I need to delete that, whatever that brackets 1 is. So backspace, and then here is where I click and drag the minute number. Hit tab again, hit OK, hit OK once more. There is our data series. So on the vertical axis, I've plotted the number of minutes into the day at which time series culminated, and the horizontal axis is just which day we're on. And you can see it ends at 14 days because we did this for 2 weeks. Okay, here's the crucial part. Right click, and you might want to ask yourselves first, do these points fall on a line? The line looks a little kinked, but if you right click, go to add trend line. This is called a best fit line. Microsoft Excel has an algorithm that it will use to find the line that best passes through those points. And there's a number of options here. You could fit a parabola, an exponential function. We want a linear fit. We expect this to be a line. So the default here is linear. Go down here and click on display the equation on the chart. Okay, I'm going to hit escape here. Did that work? Oh, my zoom window is blocking the X here, so we'll close out of there. Now, those letters are hard to read. They're small. So, oops, Control Z. What you can do is, I'm going to scoot this over here. If I click inside that cell and press Control A, that highlights all the text. I can go up here and increase the font size a couple points to make that easier. Now, I really should talk a little bit more about the equation of a line and slope, but we did that earlier in the semester. That's not really the focus here. The units of this quantity here, let's think about this. The vertical coordinate, the so-called y coordinate, that's minutes, right? How many minutes into the day? And the horizontal coordinate x, that's which day we're on. So if this quantity has to come out with units of minutes, and this quantity gets plugged in with units of days, maybe you can see that this quantity, the slope out front, the number, would have to have the units of minutes per day. Minutes per day for the slope times number of days, days cancel, and we're left with minutes. And that tells you something about the meaning of this number here. It's the number of minutes per day by which the culmination time decreases. Remember that slope tells you the rate of change of y with respect to x. It's rise over run, delta y over delta x. So each day, if we go from one dot to the next, each day the time of culmination decreases by a certain number of minutes per day. And we know that the real answer is what? 3 minutes 56 seconds. That's really precise. We know that the time of culmination does that because of the difference between the sidereal day and the solar day. But because you're taking data just using your eyeballs with these two rocks, it's not going to be real precise. So some of these dots, the difference will be greater than 3 minutes and 56 seconds. Some pairs of dots that'll be less. But hopefully if you've taken data for 2 weeks, those errors will tend to cancel. And this slope, this value here, represents kind of an average of all your data. So it's the best way to include all the information from your data. Now, 3.89 seconds. What does that mean exactly? You can do this in a hand calculator or just do it right here in Excel. I'm going to do it in Excel. 0.89 minutes. I'm sorry, did I say seconds? This is minutes per day. Let's figure out how many seconds that is. So 0.89 times 60 seconds in a minute. Oops, I guess I have to hit equals as well. I'll just round that to 53 seconds. 0.89 minutes is the same as 0.89 of 60 seconds, in other words, 53 seconds. So now I can go here and I'm going to insert a text box. Now you could do this in the spreadsheet. You can do it that way, that's fine. Type it into one of the boxes here. But I prefer to put this on the graphics, the graph itself or the plot. I've inserted a text box. Where is it? I can't even see where it is. That's confusing. Let me try that again. Insert text box. Okay, it popped up here. And I'm having a little trouble. I want to grab it and move it around. There we go. Okay, so I'm going to say the plot indicates that the sidereal day, which is the time from one culmination to the next of a star, is shorter than the solar day by, and I'll put this in bold, Control B, 3 minutes and 53 seconds. Now we know that more accurately it's 3 minutes and 56 seconds. I showed you that in Google. Let me drag this down so we can see everything. Maybe I can increase this font just a little bit. But hey, that's really close, 3 minutes and 56 seconds. So you don't need to fake your data, tweak the number. As long as you get something roughly equal to 4 minutes. Write down the nearest, put your answer to the nearest minutes and seconds as well. But I'm not looking for, if you write down, if the number you come up with is 10 minutes, well, then you did something wrong. You were probably, I don't even know what that would be, maybe really sloppy with your measurement of culmination. But hopefully you get something close to 4 minutes. And I will be looking for this statement. You can put it on the plot, or you could type it off to the side in the spreadsheet. Just make sure it's nearby. We don't need to do a percent difference for this one. We know it's supposed to be more like 3 minutes and 56 seconds. I'm just looking to see that it's similar. And I will look for the equation of the line here. I may even check your data that it matches your plot. So obviously your numbers will be different because you're not doing Sirius, because you're not up at 4 a.m. You would have done Fomalhaut or maybe Rigel, depending on how late you were up. And that's it for this part of the lab. So in summary, this lab clued you into the fact that the sun's altitude is changing every day, and that's because the declination of the sun changes. It's moving around the celestial sphere on that ecliptic. Sometimes it's above the celestial equator, sometimes it's below. Right now it's below and heading towards its lowest point at the winter solstice. And you've also observed that the stars culminate or cross the meridian a little earlier each night on a 24-hour time scale. And that's all. Good luck.